Hi, so today we'll study maximum likely estimation on section 6.1. So we have a data. So this is data with size n, and this data comes from a distribution with a density, right? Density f. But we don't know the density, but we can actually maybe assume that this unknown density belong to a family, parametric family of density. So parametric distribution indexed by zeta in omega. So this is a parameter space, right? Parameter space. There's exists zeta null. So this is a true parameter, such that this unknown density function is actually is one particular case of the family in the family. So belongs to the family, right? Indexed by zeta null. Also, we will assume that the densities have common support. That is, this is support, right? So of random variable x does not depend on zeta. So under that setup, we can develop likelihood function. So likelihood function is nothing but joint density. But joint density is a function of x. So this is data, right? Data. And this is a parameter. But we just view that likelihood is simply treat data given and just view it as a function of parameters, which is zeta, right? Function of zeta only. Okay. And under the IID setup, under the IID case, joint density is just a product of the marginal density function. And then likelihood function, the maximum likelihood estimator is the one that maximizes the likelihood function. So another way of saying this is zeta hat is a argmax. So that means this is kind of argument, okay? Argument in the function. And so what we are going to study in this chapter is first MLE converges in property to true parameter zeta null. That is the section 6.1. And then the MLE has an approximate normal distribution, and MLE is asymptotically efficient. So asymptotically efficient means that asymptotically achieves the minimum variance among certain class. So these two will be covered in section 6.2. So to discuss, to prove the convergence in priority, we are going to, I'm going to first introduce some very famous famous concept which is called Kullback-Leibler information. So Kullback-Leibler information is very popular in information theory and computer science and things like that. So given that we have two density function, so it's kind of distance. So it's kind of distance between the two density function, but the way it is defined is this one. So if given given f0, how much f1 is far away from f0, something like that. And so so that is this is just the definition, Kullback-Leibler information. And this information, so this notation, so this, what is this? This is basically expectation, right? Expectation with respect to f0. So that means we have a log. So this is just a function of random variable, right? So just this, for this particular random variable, we have a density function evaluated f0. So that is the definition of this notation, Kullback-Leibler. And interesting property is that this Kullback-Leibler function information distance, Kullback-Leibler information is non-negative, and with equality if and only if they are right. So equality means that this distance is 0 if the two density functions are equal with property 1. Okay. So to prove this inequality, Shannon-Kolmogorov information inequality, we are going to use Jensens inequality. So Jensens inequality is quite well known inequality. So if you have a convex function, and then if you have this, right? If you have a this, so if you consider this, so this is the what? This point is, one way to understand this is that this you can view that this one is average expectation. This is just random variable, right? Random variable taking anywhere between the two points, and then this one. Oops. Okay. Sorry. So then this one. This one is what? This one is function g of, right? Because this is gx. This is graph is y equal gx. So g of ex, right? And this is g of particular ab. So this is g of a and g of b. So this guy is g of expectation of g of x. So that's how we can understand this, because the graph shows that this one is always bigger, right? So but if this function is strictly convex, then we can achieve equality if and only if this is just degenerating random variable. So that's the given Jensens inequality, and we are going to use this Jensens inequality to show this Shannon-Kolmogorov information inequality. So this Shannon-Kolmogorov information inequality is basically using this particular convex. So this is a strictly convex function, right? And so we can use Jensens inequality here. So this is Jensen. So this is definition. Okay, this is definition. So we just reverse f1, f0. So that's why we have minus, and then this is basically what this is expectation of phi of x, right? And this one is what? Minus phi. So what? Sorry. Okay. So this the whole thing is expectation of phi of x, and then right. This guy, okay, right. This guy is phi of expectation x. So x here is this is a, I mean, y. Okay, so maybe we can call it y, and then right. So this applies this, and then why this is because if you consider this integration, so this is actually integration, right? This is, the expectation is integration of f1x divided by f0x times f0x dx. So then if you have a common support, then we can have this one is equal to 1 because it's integration density function, right? So this one becomes equal to f1x dx. So that's why it is equal to 1. So and then log of 1 is equal to 0. So that's why we have 0. And so with equality, if and only if this random variable y equal to 1 constant, right? And this constant should be 1 because they are both density function, so should be equal to 1. So that's why this one. So that proves the Shannon-Kolmogorov information inequality. So now I'm going to briefly talk about identifiability. So identifiable, okay. So the model density family of density function is called identifiable if basically if this. So another way of saying is if two density functions are different, then the parameters are different, then the density functions are different. Okay. So that is the definition of the identifiable. So one property of the identifiable distribution is that this guy, so m given zeta null, right? Given zeta null, you can write this is a function of zeta only, and then unique maximum. So what is this? By the way, this one is if you compare this Kullback-Leibler function, then this one is nothing but minus minus k zeta null, okay, maybe f null. Let me see. So f is over here, right? So minus f null, and then f zeta. So that is the definition. So because we know that k f0 f null f zeta is non-negative, so that means this m zeta should be always